My pleasure to welcome you to the 2019-2020 season of the Math, Computer Science, and Physics Symposium Series. At this time, selected Tuesdays, we'd like to have our students, we'll have faculty, we'll have alumni come back and present to you about their research, about their experiences. Alumni will sometimes come and talk about their experiences after graduation in grad school and in their careers. To try to broaden all of our experiences just a little bit. We'll be looking, as a side note here, we're going to be looking this year at using some of the Tuesday slots here that we do not have speakers to show some movies, videos that may be appropriate, educational, informative, and entertaining. And fun. Yeah, and fun. Definitely the fun part. And also have cookies. Which really is the key factor for all of this. It's my pleasure to welcome back to the symposium Darby Kramer. Darby is a fourth-year physics major and veteran of the symposium series here. Darby had an RU at Geneseo in New York and will be talking to us about using the PNLF to determine distances to nearby galaxies imaged by the Hubble Space Telescope. And RU tidbits. Please welcome Darby.
Hello everyone, as you said, I'm Darby Kramer and I'm a physics and math double major. It's okay. It was last year. But like you said, I'm going to talk to you guys about my RU experience this summer. I'll give you a little bit of overview first off, just so you have an idea of what I'm going to talk to you about today. I'm going to give you some background first on how I got into the setting of doing this research, where I did it at, and then I'm going to give you some background contextually about the research that I did. Then I'm going to talk about the data collection, which was a search for objects called planetary nebulae. And then I'm going to tell you about how we use that data to generate and study something called a planetary nebula luminosity function, or PNLF for short. I'll give you my results, and I will share the overall RU experience that I had as well. So first off, I started last winter, in November, December. I was looking at RU programs to apply to. For those of you who don't know, RU stands for Research Experience for Undergraduates. There are several subjects that the National Science Foundation funds these for. Mine happened to be physics, but I know there's like bio and chemistry, all kinds of stuff. So basically it's government-funded research that you do at mostly larger institutions. I applied to 8 or 9 programs over the course of last, probably winter break, into the spring. And I actually only got accepted into 1. So it felt a lot like applying to a school almost, applying to college or even grad school, because I had to send like an unofficial transcript. I needed to have a statement of intent, or I had to have like a personal statement, something that told them why I wanted to go there. So it was very rigorous, and I almost didn't think I was going to get into one, and I got accepted very late in the process, but I was happy to get one. And I ended up accepting the position in the program they called it was SURGE, which is Supporting Undergraduate Research at Geneseo, but it's their form of an RU program. And it was located at the State University of New York in Geneseo, New York. It's a small town, almost about the size of Waverly, I think. And I lived on campus for 10 weeks over the summer. I got a stipend. It actually was a pretty good stipend. I've never made that much money in the summer, so that was pretty nice. And I got to look at cool stuff over the summer too. So my advisor was Dr. Ann Helleran. She's actually a member of the Legacy team, which I will be discussing a couple times in coming slides. This is just an image of campus. The picture is probably taken inside the Science Center. This is the green, they call it, I think. It's a pretty campus, but it was on a hill, and I had to walk up the hill every day to go to work, so that's kind of rough, but got me in shape. So this is more into the research that I did. This project started way before I got there. Dr. Cohen started it with one of her freshman students who actually she's my age and was working on it with me when I was there. So before we get into what we research, I'll give you some background about why we're researching what we are. So it's something called the distance problem. So in space, things are really far away. Space is big, right? There are some things that are closer than others, and some things that are fairly close, relatively close, we can figure out how far away they are using geometry. We can look at them and observe them, and we can use parallax and triangulation to find out how far away they are. Once we exhausted that method, and there are still several things, obviously, like billions of things, farther away than that, we had to figure out another way to find out their distances. So after observing things close up, we got to see lots of different types of objects and characterize them as classes. And so this equation is fairly simple, but it's called the distance modulus, and we can use characteristics we know about these types of objects to determine how far away they are based on how they look to us and how we know they are, like how the characteristics we know that they have. So what you need is some type of distinguishable object that we know something about. We know how bright it is intrinsically. We also need a way to measure how bright it looks to us. That's dependent on the distance it is away from us. So we call that the apparent magnitude, how it appears to us. And the third thing that we need is, like I mentioned earlier, the way that we can determine what it actually is, how bright it actually is, what its intrinsic values are. So some examples of these objects are supernovae. If we can determine what type of supernova it is, we can say, well, okay, it's supposed to be this bright, this is its absolute magnitude, and this is how it looks to us, so this must be how far away it is. Another type of object that we can study for this purpose, they're called Cepheids. They're also called variable stars. Their brightness varies, and their brightness actually varies according to, we can tell how, what their absolute magnitude is based on their period at which they vary. We can study just a whole galaxy. If there's a grand design spiral galaxy, we assume that they have certain bulk brightnesses that we can say, okay, this looks this bright to us, but we know how bright it is, so this must be how far it is roughly. The fourth object here on this list is a planetary nebula, and that's what we will be discussing today. It's the objects that I studied this summer. So I will tell you a little bit about what planetary nebulae are. They are stars that are from 0.8 to 8 solar masses in size, and they are actually dying stars. So when these stars die, they start to release their outer layers of gas. And the inner core runs out of its hydrogen fuel and starts to fuse helium. And so that actually releases ultraviolet rays that excite the gas that is expanding outward from the star. And so it's kind of like, Dr. Figueroa told me to use this analogy, like UV rays, or UV like black lights. The reason they glow like that is because there are excited atoms from UV, like emitting those photons. So like your shirt glows when you get a UV light shine on it. So that's kind of what this gas is doing. They're emitting certain photons, and they only do this for a short in space-time, which is 10,000 years, because that gas becomes so diffuse after a period of time that it no longer displays these characteristics. But the main thing that we look for when we look at these objects are their characteristic emissions. So as I said, they get excited by the ultraviolet rays that come from the core, which is a white dwarf. And one of the main emissions that these things are characterized by are called O3 emissions, which are energy transitions from doubly ionized oxygen in that gas that's expanding. It emits a green photon. The wavelength is like 500 nanometers. So that's why some of these, I put this picture up here because they definitely look green. At least those three middle ones there look green, because that's kind of the these are green objects. When they're close to us, they look more complex and different colored. When, like, if they're in our galaxy, but when they're outside of our galaxy, they just look green to us because of that concentrated O3. They also had another characteristic emission, H alpha, which is it's a Balmer transition. It's from N=3 to N=2. It's a red photon, so it's 657 nanometers. But we mainly focus on the O3 green color that's emitted by these things. So I wanted to make sure I stress, these are images that are close-up images of these things. So these are probably within the Milky Way. These don't look like this when they're outside of our galaxy. So once we saw the ones within our galaxy and we said, okay, this is what they look like, this is what their spectra look like, then we can search outside of the galaxy and check other objects and say, oh, this is probably a planetary nebula too. And so that's kind of why we use these objects, because we can distinguish them when they're not inside our galaxy. And it's useful for distance calculations. So once we define planetary nebula, we can search for them in other images, like I said, outside our galaxy. And our team was using LEGAS images. So LEGAS stands for Legacy Extragalactic Ultraviolet Survey. My advisor was a member of that team. The survey was done years ago by the Hubble Space Telescope, but we were able to reuse the images for a different purpose. And these images are monochromatic, meaning they are taken in one wavelength. And the goal was to load them separately into this software called DS9. We had to load a red wavelength, which was 814 nanometers, a green wavelength at about 555 nanometers, and a blue wavelength at 435 nanometers. So these images are they look just black and white. They're singly chromatic. They have one color. They represent one color, but they're black and white. So we load these three types of images we layer them on top of each other based on their coordinates in DS9, and we can add false color to them. So we add red, green, and blue, so that it looks red, green, and blue to our eyes. And we have to balance those colors until the center of the galaxy that we're looking at is white. Because red, green, and blue in light makes white. So we would load them up, and once they were loaded and calibrated, we would zoom in on them really far so we could see individual pixels. And as you can see, there's each one of the colors on here, each one of the color dots is a star, pretty much. So we would zoom in and try to look at every star. And if there's a green dot that stuck out to us, we would mark it with a green circle. And we would scan the entire image manually, looking for these green objects. And once we got through the image, we had all these circles everywhere. We could export those circles as a region file. That's how we kind of created our data. Once we had this huge list of green circles and their coordinates, we could actually use the LEGAS catalogs to match objects that we marked with the objects in the catalog. These catalogs, LEGAS made these catalogs based on these images. So they looked at every object in this picture, in any galaxy that's on there, and they logged the photometric data. So they logged the magnitudes in each color. So they logged the red magnitude, the green magnitude, the blue magnitude. They logged ultraviolet magnitudes and their uncertainties. So these catalogs are huge files. And so we wrote a Python code that matched our coordinates with their coordinates. And it spit out the photometric data for the objects that we marked, which was what we wanted. We want to look at the photometric data for these objects. We want to make sure that they're green. So after we got our matches, we had to kind of go through our sample that we collected and sort it and clean it up pretty much. So each of the candidates that we marked, if they're a good candidate for a planetary nebula, they need to have red, green, and blue magnitudes. If there was a 0 listed for like a red magnitude, we would kind of second guess it and go back and check and see if it looked really good. The images that I have here, these are really good examples of, it's hard to see here probably, but they're really good examples of candidates. Some of the candidates we would mark didn't look quite as uniform or like bright as these ones. It depended on the image quality. But, so we wanted to make sure that they were mostly green, but had blue and red also. And this plot here, this fuzzy plot, there's color, and color magnitude diagrams on here. This upper left one is a color diagram. And it basically takes, all these plots are basically to assess its greenness. Make sure that it's more green than other colors. So all of these black dots in each of these plots is every star in the galaxy. It took all the data, the photometric data from every star and plotted it on this plot. The red dots are our candidates that we marked. So it was able to take the photometric data for those and color them red. So these things are supposed to cluster in these plots. That's why we made them. So as you can see, they cluster pretty well. They're supposed to cluster in the bottom right of that top one and like all those other areas in the other ones. But if they stood out, like there's a couple here and a couple on that one that aren't in the cluster. So that's what we did this for, to check and see if they didn't cluster. And then we would be able to identify what those candidates were and go back and look at them again and see, is it just a pixel? Like, is it actually an object there? Did we hit the right object? And so forth. So we would do that, we did that more than one time because we had to keep going back and looking at it and deleting candidates and then regenerating these plots. We did it so many times. A third way that we would clean our sample is, as I mentioned, we had O3 and H alpha emissions that are characteristic of these objects. Sometimes Hubble had actually given us images, monochromatic images, as I said, of O3 emissions and H alpha emissions. So they're still visible wavelengths, just a little bit different, narrow bands. So they needed to have a presence in these pictures that were there if they were present as well. So after cleaning up the sample as much as we can, we studied the planetary nebula luminosity. This was derived by Robin Chergulo in 1989. And it basically is a description of the distribution of planetary nebulae in a galaxy, any given galaxy. They're supposed to be, so magnitude is kind of a funny thing because the smaller the number, the brighter things actually are. So the brighter ones exist on this side of the plot. So there are a lot fewer bright planetary nebulae than there are dim ones. And so the bright ones we use to characterize the galaxy. So this fit, these dots, this is Andromeda Galaxy. I just found this as an example. This isn't our data. But those dots up there is just a histogram of the spread of the candidates and their magnitudes, their their apparent magnitudes, excuse me. And it's in the O3 magnitude, O3 wavelength, which is the characteristic emission of these objects. And this curve is a curve fit to that function. And the whole purpose for this curve fit is so that we can get this x-intercept here, which is the theoretical brightest planetary nebula in that galaxy, which is what we're going to use for our distance calculation. So, yeah, this is just a general example, but I will show you how it applied to our data. So this is NGC 4449. It was probably our best galaxy in terms of the images looked good, and we had lots of candidates. We had a good sample size. And it's on a logarithmic scale, if that's confusing anybody. But you can see that this function fit our brightest candidates very well within the uncertainties. And we were able to determine that the apparent magnitude of the brightest candidate in this galaxy was supposed to be about 23.5. So that was our number. That's the number we were shooting for. That's the whole reason we marked all those green circles. And all these other ones, so I'll talk about completeness. All these other circles that don't follow the curve, that's on purpose, that we know that's supposed to happen. Because as candidates get dimmer, as things get dimmer, we can't see them as well, right? So we're not expected to catch all of the dim candidates in that galaxy, because we can't see them all. So that's why it drops off like that. Just to explain that. And then, so the whole purpose for this function that we fit it to is to plug in a number to that distance equation that I showed you guys earlier, so we can calculate how far away these things are. So we need the brightest apparent magnitude of a candidate, which is the number we got from that plot, from that curve fit. And then m star is the theoretical absolute magnitude. So this is a number that's constant. We don't for sure know it, but several papers have been written about it, and the number we used was negative 4.81 for the absolute magnitude of these things. So that's how bright they are, or that's how bright they look at 10 parsecs, right? That's the absolute magnitude. So that's the constant number. If we know that these things are planetary nebulae, that number is correct, assumed to be correct. So we just needed two numbers, and we were able to plug them into this equation. And even though we studied several galaxies, like tens of galaxies, there were only 4 galaxies that had sample sizes big enough to actually analyze, and we thought that had sample sizes to represent the galaxy. So the 4 galaxy names are listed here, and the distances we calculated using that equation I just showed you are in the middle column. And the accepted distances were acquired from a recent paper. But I think there's several, like hundreds of people that contribute to that data. So those are kind of the distances that we think these galaxies actually are located at. And they have uncertainties. And these are all in megaparsecs. Megaparsecs means millions of parsecs. And there's either 3 light years